Okay, guys, in this lesson, we're going to learn how to graph and write exponential functions. An exponential function is where we have our x variable is the exponent. So our most basic generic equation is f of x equals ab to the x, where your a is your initial value, which will come in handy when we do word problems, and your b value, the base of your x, which is the exponent, is called the growth or decay factor. Notice our graph, our exponential graph, has a curve in it. Most exponential graphs has an arcing shape. It is curving. F of x equals 2 to the x is known as the parent function, meaning it's the most basic function for exponentials. All exponential functions has an understood asymptote, which is a line in which the graph gets very close to but never touches or never crosses. In this example, our parent function, when we have f of x, a, b to the x, our very simple exponential equation, our asymptote is always going to be y equals 0. So our graph is never going to go past y equals 0. Let's compare and contrast exponential to linear functions. We know that a linear has a constant rate of change, and in this example, from 2 to 4 is plus 2, from 4 to 6 is plus 2, 6 to 8 is plus 2, and 8 to 10 is plus 2. And our x values are increasing by 1. So this has a constant rate of change, and we use the variable m to represent that slope value, which is going to be 2. Exponential functions do not increase at a constant rate of change. Instead, they increase at a constant ratio over equal intervals. And when I say equal intervals, I'm talking about our x values for this course is going to increase consecutively by 1. So all we have to look at is our output values and see the pattern of how we're going from 2 to 4, 4 to 8, and so forth. So instead of increasing by adding the same, we are going to increase, in this case, by multiplying by 2. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So because we have a constant ratio, we have an exponential function, and this would be the b value of the equation. In this case, b equals 2. Remember, for exponential functions, it's f of x equals ab to the x. Now let's compare those rates of change again. Remember, linear functions change at the same rate. In this case, we're going up 1, right 1, up 1, right 1, and so forth. In our exponential, as the x values increase by 1, my output values are increasing times 2. They are increasing exponentially. Now let's look at our domain and range. For this linear function, our domain is all real numbers, and our range is all real numbers. Our graph is continually going left and right, as well as going forever down and up. In our exponential graph, we can see that our domain is all real numbers, but the range is going to be different than in a linear. It all depends on our asymptote of what our range is. So our asymptote is y equals 0. So the least value that our range can be, which are your y values, is going to begin above 0. 0 is not included. None of your y values will ever be 0 in this function here. And then it continues forever to positive infinity. So this is our range for this example. The range in exponential is always going to include your asymptote. Let's look at in behavior. We can see in this graph as x approaches negative infinity, f of x approaches negative infinity. Then on the right side of the graph, our graph goes forever up as well. So as we go right, the graph goes up. Let's look at our exponential. I'm going to jot in our asymptote. On the left side of our graph, as x approaches negative infinity, the end of the graph, f of x, approaches my asymptote. As we go left, the blue line, our graph, is approaching our asymptote of 0. On the right side of the graph, as x approaches positive infinity, as we get larger, as our x's get larger, our output, our f of x, also get larger. So note that when you're doing in behavior for exponential, either the left side of the graph or the right side of the graph will approach the asymptote. Here, let's look at the linear intervals of increase and decrease. In this case, you can see our graph is continually increasing. So our interval of increase is all real numbers. Our interval of decrease does not exist because this graph is never going down. This is true for our exponential graph. It is either always going to be increasing. In this case, it is. So we have an interval of increase across our x values, are all real numbers. And this graph is never going to decrease. It's either going to do one or the other. So this is where linear and exponential graphs behave very similarly. Let's take a look at how we can look at a function table of values and determine if it is exponential. We can see that our y values are decreasing here. But let's see if we are decreasing by a constant rate of change or a constant ratio. So I know from 128 to 64 and from 64 to 16 is not the same amount. So I know this is not linear. Now let's find out what, if it is exponential, we are going to compare 64 to 128. So I take my value and put it over the previous value and I continue down. And I'm going to simplify each of these. And I can see that I have a constant ratio. I am multiplying 128 times 1/4 to get 64. 64 times 1/4 is 16, and so forth. Remember, multiplying by a unit fraction is really dividing by that denominator. So this would be my multiplier. My b value is 1/4. Let's look at our second example. We're going from 8 to 24, from 24 to 72. So this is 8 times 3 to get 24, and 24 times 3, and 72 times 3. So sometimes when it's increasing by an integer here, it's easy to spot. But again, we can do our ratio. 24 over 8, 72 over 24 to 16 over 72 and so forth. And we would divide these out and we would get, they would all simplify to 3. So our b value, our multiplier for this exponential function is 3. So this is how you determine your b value in your equation. Let's identify, so you can pause the video and let's identify to see if these function tables are linear or exponential. So from 2 to 4 and 4 to 6 and 6 to 8 and 8 to 10, I can see I'm going up by 2. So sometimes seeing if they increase at a constant rate of change is maybe a little bit easier before you do your ratio. And so this is going to be a linear function. Number 2, from 8 to 16 and 16 to 32, it looks as though we are multiplying by 2. So sometimes you can just simply see it and you may not need to make that ratio. So this is exponential. 3 to 6, 6 to 9, 9 to 12, these are increasing by adding 3. So this is a linear function table. From 2 to 4, 4 to 8, 8 to 16, it looks like we are multiplying again by 2. So this represents exponential. And now we're decreasing here, and it looks as though, I think this is going to be exponential. So this gives me 1/2, and then I can try 16 over 32. That is 1/2, and 16 over 8 would be 1/2. So this is exponential, where the b value is 1/2. Let's write this. Our b value here would be 2, and the b value for this exponential is also 2. Here in the linear, this would be our slope, and for linear, our m is slope. Okay, the last one. From 3 to 9, 9 to 27, 27, I am increasing definitely, and I am increasing exponentially. I am multiplying by 3 each time. So this too is exponential, where our b value is 3. So linear functions have a slope, which means we have a constant rate of change of adding or subtracting. Exponential has a constant ratio where we are multiplying either by a whole number or our rational number, a fraction. Okay, let's graph a few of these. Let me change colors right quick. So we're just going to practice graphing by hand, and we can use Desmos in just a minute. So I'm going to plug in -2 for x. So we have f of x equals 2 to the -2, which means we have 1 over 2 squared, which gives me 1/4. Then we're going to plug in -1. This is going to give me 1 over 2. When I plug in 0, 2 to the 0, anything raised to the 0 is 1. And then when I plug in 1, I get 2. And when I plug in 2 for x, 2 times 2 is 4. Now, let's talk about this. We have f of x equals a times b to the x. My b value in this case is the 2. So b is 2. This is your multiplier. I'm going 1/4 times 2 is 1/2. 1/2 times 2 is 1. 1 times 2 is 2. And 2 times 2 is 4. Now, what about the a value? We do have an a value. It's just the understood 1. We don't have this written in here. So the b value, your multiplier, is the base of your x. So remember that. Your b value is your base, b for base, of the x. So 1 is going to be our a value, and remember our a value is our initial value, which is 0, 1. So we're going to plot 0, 1, and then we have 1, 2, and then we have 2, 4. So this is going to quickly. And then we are decreasing. We're getting smaller and smaller. I'm going to write in my asymptote of y equals 0. And then I have -1, 1/2. And then I have -2, 1/4. And it gets closer and closer to the asymptote. And this side increases exponentially. Okay, and we just identified here is our A was 1, our B was 2. Here's our graph. The domain is all real numbers. My x values can be anything. My range, however, is limited with the asymptote. The least value that y can be is 0, and it can't even be 0, so I'm not going to include it. and then it goes forever to positive infinity. My y-intercept is 0, 1. My interval of increase is all real numbers. Our graph never decreases. Our end behavior, as x approaches negative infinity, f of x, the end of this graph, the end of the blue graph, approaches 0. Then, as x approaches positive infinity this way, f of x, the end of this side of the graph, approaches positive infinity. My asymptote is y equals 0. Now let's find the average rate of change between 0 and 3. So I have 0, 1, and then we have 3, looks like, 8. So I'm going to go rise over run. Whoops. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 7 over 3. Okay, let's graph this function. We're going to plug in again our x values, start with -2. So this tells me that I need to reciprocate my base. So I'm going to have 2 squared, so this gives me 4. Then when I plug in -1, I'm going to reciprocate my 1/2 to 2. When I plug in 0, I get 1. When I plug in 1, I get 1/2. And then when I plug in 2, 1/2 times 1/2 gives us 1/4. So I'm going to graph my asymptote here, y equals 0. And now let's plot these points, -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. Notice this graph is decreasing. So the a value in here, remember, f of x equals ab to the x. My b value is the base of x, so my base here is 1/2. That's our multiplier. That's why we are decreasing. We're going, let's look back at here. We're multiplying 4 times 1/2 to get 2, 2 times 1/2 to get 1, 1 times 1/2 is 1/2, and so forth. So we are decreasing in value. The a value is the understood 1, which is my initial value 0, 1. My domain, just like with linear functions, is all real numbers. My range is restricted with our asymptote. The least value, it goes to 0, but it doesn't quite get there. And the output value is from 0 all the way to positive infinity. But again, 0 is not included. My ordered pair for my y-intercept is 0, 1. My interval of increase, we have none. My interval of decrease is all real numbers. Now let's do end behavior. As x approaches negative infinity, so here's negative infinity. As x approaches negative infinity, f of x, the end of the graph, approaches positive infinity. As x approaches positive infinity, as we go toward the right, as my x values decrease, the output values approach the asymptote of 0. My asymptote is y equals 0. And let's find the average rate of change between -3. So -3, it looks like it's right here. -3, 8. And then we have 0, 1. So we're going to have a negative average rate of change. So we're going down 1, 2, 3, 4, 5, 6, 7. Let me say that again. 1, 2, 3, 4, 5, 6, 7. And to the right, 1, 2, 3. So our average rate of change is -7 over 3 over that interval.